Hi viewers, this is Sri Ramalu. So my YouTube channel is s.s space physics. So today's topic is boundary conditions. So these are the boundary conditions in electromagnetic induction only or electromagnetic waves only. Why? Because already we have the separate boundary equations or conditions in electricity and in magnetism. So it is a combined effect. Okay, so let me start. Right, when a free space electromagnetic waves is incident upon a boundary between different media, part of it is reflected and remaining is refracted or transmitted. Right, so we know already. Suppose this side is one medium and this is another medium, and suppose EM waves are coming like this, then what happens when they strike to the boundary? Part of EM waves may be reflected like this and part of EM waves may be refracted downwards or transmitted. Next, characteristics of above can be explained by Maxwell's equations. So these waves characteristics can be explained by the Maxwell's equations. So how many equations? 4 equations are there. Here boundary conditions also 4. 2 are belongs to the electric field and 2 are belongs to the magnetic field. So in electric field, let me start. Right, boundary conditions for electric field. So boundary conditions for electric field, let me explain. Right, the component of electric field parallel to the boundary is continuous across the boundary. Right, so parallel to the parallel or tangential also we call. So see here, it is a substance. There are the two substances. Let it is a one substance and it is another substance, and these two substances are joined here. Okay, so when they are joined together, then here boundaries or interface will form. And see here, they have the separate refractive indices. So they have the permittivity and permeability separately. So that means this material is different than this material. And see, this is the boundary. Why? Because boundary means this object and this object are meeting at this point only, at this plane only. So that is called boundary. Now what? Once again, component of electric field parallel or tangential to the boundary or interface. So boundary, another name is interface. Interface means the region where the two media meets, that is called interface or boundary, is continuous across the boundary. Continuous means same everywhere, that is a continuous. Discontinuous means not same, it is a different at different places. So continuous means same. So what is the same? Electric field is same. Which electric field? Tangential or parallel electric field is same. What is a tangential or parallel electric field? See here, for example, it is a substance like this only, and let me join another substance. Okay, here it is boundary. Or we can imagine like this also. Suppose it is a substance. Okay, it is substance, and outer region is also another substance, and these two are meeting at this point. Okay, suppose the electric field is coming like this. Electric field is coming like this. Then what happens? Are either coming, it is like this. Then part of electric field will be like this, and the remaining part is in this direction. So see, this is a parallel to the boundary, this side, and it is perpendicular. Or we can show like this also. Okay, or we can show downside also, going outside. Okay, let me start the lesson. Consider a loop spanning. Spanning means expanding or existing. Spanning or expanding. or spreading. Spanning means spreading. Okay, spanning means spreading. So span means spread. Consider a loop spanning the interface between two media. So two media, epsilon 1 mu 1 and epsilon 2 mu 2, being their permittivity and permeability respectively. Okay, so its permittivity and permeabilities are mu 1 epsilon 1 mu 1 to it, so mu 2 epsilon 2. Let E1t and E2t be the tangential components of electric field intensity in the two media at interface. Okay, at interface, what are these two things? E1t and E2t are two tangential component. Tangential component means here let electric field is coming like this. Okay, so here through this boundary is forming here only. Why? Because it is one object, it is another object. These two objects are joined at this point only, so that is why it is called boundary. Okay, so here let me make it big in size. It is one object, it is another object, and let the field is coming like this tangentially. So here also comes and here also comes, here also comes. When we expose to the electric field, so electric field lines are downward only. But what we need the electric field at the boundary only. Okay, so field is coming means it may touch to the boundary, right? Suppose it is one object and it is another object, and join them together, then what they forms like this. So this is in this manner. Here it is interface, and if you expose the electric field like this, then electric field also penetrate like this, and through the boundary also electric field passes. So through boundary passing means it is a parallel to the boundary, so or it is called tangential, just touches it boundary. Okay, and here E1t and E2t means two tangential electric field. One is what? One is belongs to this subject and other one is belongs to this subject. One is belongs to this subject is E1t to this E2t. Okay, so it is electric field, tangential electric field for this object, and it is a tangential electric for this object. Now the necessary boundary conditions can be obtained by applying Maxwell's equations derived from Faraday's law. So if you have to calculate the electric field at the boundary, then we have to apply which law? It is a Maxwell equations only, but it is in integral form, and this Maxwell equation is derived from where? It is derived from Faraday's law. Okay, so it is Maxwell equation. And what is this integral over a closed loop? E dot dl is equals to minus integral dou b by dou t dot ds. It is dl is the length, ds is the area. Which area it is? Area of a closed circle. So for this what we have to do? We have to take a closed circle. Now listen carefully. This point if you understand, then you can understand all the boundary conditions easily. What I am saying, electric field lines comes like this. Yes, and through boundary also electric fields passes this side and this side, this side and this side, this side and this side. So if you consider one loop here, right, like this at boundary only, if you consider a small loop, okay, so let its length is L or DL. This length is also DL. Okay, and see inside area, this is the area, let small area ds. Okay, that is a small area inside which we consider loop, so that loop area is ds. So here it is a loop is also given, see clearly it is a loop. Okay, see arrow mark is given. Okay, and when we compress this loop, which loop? See already given in diagram, this loop if you compress, what happens? Its area slowly decreases, And again, if you take if you compress very nearer to the boundary, this area is what approximately equal to 0. That means this term becomes 0. When this term 0, this total term 0, right? Then integral E dot dl is equals to 0. That point we need. Okay. In the limit in which the width of the imaginary loop becomes 0. Its width. So this width, which we consider. Suppose, once again see here, let it is a boundary. Now electric field is coming like this on either side. This side electric field, already I told you, E1t. This side electric field, E2t. Okay. And if you consider here one loop, small loop, and if you compress if you compress this loop, then what happens? It becomes very narrow. Then its area is 0. Okay. So like this. Now the contribution to the integral around around the loop C from the narrow ends becomes 0. Yes, right? So over a closed loop it is 0, as does the integral of magnetic field across the area bounded by the loop. So see, this is what I said there, integral E dot dl is equals to 0. I said dl is the length. If you take the side length, this length as see, it is a boundary, and we consider one loop here. This side length is dx. This side length is also dx or delta x. Okay, so instead of taking dl, if we take as a delta x also distance, small distance. See, then electric field into distance. Our integral formula is also integral over a closed loop E dot dl. Electric field into length, electric field into length, electric field into length. And y minus is taken. Y minus is taken. See here. Here minus is because of this side. So it is a boundary. Okay, it is boundary. This side values we have to take it as negative, and the right side values we have to take it as positive. This side values, which values are there? Even one values are there, and this side are 2 values are there. Okay, so E1t into delta x plus minus E1t delta x plus E2t delta x is equals to 0, isn't it? Then bring this minus that side, then it becomes minus. That is a minus. It has come like this only. Okay, now that is the tangential component of E is always continuous at the boundary. So when the term is a 0, or we can write like this also, E1t into delta x is equals to E2t into delta x. Delta x cancel. E1t is equals to E2t, right? E1t is equals to E2t. It is called continuous electric field at the boundary. Okay, it is a tangential component of electric field is always continuous. Next, second one, in the presence of surface charge at the boundary, the normal component of electric displacement changes abruptly by an amount equal to the surface charge density. Okay, what he is saying, the presence of surface charge density, surface charges. So on the surface charges, if the charge is present at the boundary, then what happens? Normal component of electric displacement changes abruptly, means they cannot be 0. Some value we get. D means we know D is equals to epsilon naught into E. So that means D is nothing but electric field only. Alright. Okay. So D means what? It is simply, it is a electric field. D is equals to epsilon naught into E. And here normal component we have to take. So in the previous, in above, in tangential, we have taken two objects like this and they are joined in this manner, and we said it is a boundary. Here also we have to take same thing, but here electric field in previous one tangential means like this, electric field has come like this. Now electric field, it is, this field is parallel to the boundary. Now which field we have to take? Normal field means perpendicular field. So field will come like this now. So this field is, see, it is perpendicular to the boundary, isn't it? So perpendicular to the boundary field, what we call? Normal field we call. Okay, so if it is a boundary, now electric field comes like this. So now for this, what we have to take? We have to consider a small area, right? Small area, and here small box we have to consider. That box is called pill box, right? What is called? Pill box. Pill box means, you know, the tablet box, tablet size box. Tablets, pills means tablet size. Okay, now let me explain. Consider a cylindrical pill box across the surface. Okay, here it is, see, it is cylindrical pill box. Let d1n and d2n be the normal components of electric displacement. So d1 is electric displacement. Electric displacement. Necessary boundary conditions can be obtained by applying Maxwell's equations derived from the Gauss law for electrostatics. Here which law we are applying? Gauss law. But in tangential we applied Faraday law, right? Faraday's law we applied, but now we are applying Gauss law. Okay, Gauss law, integral form of Gauss law. Okay, Gauss law is what? Integral d dot ds is equals to rho dv. In the limit that the length of the pill box approaches 0, the integral over a curved surface also approaches 0. What? See this, its meaning is listen. Limit means what we have to do? We have to compress the pill box. Okay, suppose pill box means like a tablet, just now I said you. Suppose here, what is this? Let it is a one object, it is another object, and it's their boundary. At this, what you have to consider here? We have to consider one pill box like a tablet. I consider like this. Okay, and this side area A, this side area is also A, and this, it is a curved surface. Why? Because cylindrical shaped pill box we have taken. So it is a what? It is cylindrical shaped. Then it is curved. For curved also, let its area A. Now what you have to do? Compress it. Means bring these two ends nearer to the boundary. When you compress, this width, what happens? Decreases. Then area of the curved surface is 0. But this surface area and this surface area never 0. Okay, once again. So this diagram only I am explaining this side. I will show again the diagram. Let it is one object, it is another object. These two are joined at this point. Then it is called boundary. At this point, consider one cylindrical shaped pill box like this. This side pill box area is A, this side pill box area is A, and this curved surface, why? Because it is cylinder, curved surface area is also A. Now compress this end and this end. Then what happens when we compress two ends of the pill box? Then it becomes very small, isn't it? It comes very nearer to the boundary. Then this curved area, what happens? Curved area becomes 0. But this area, its area, this surface area never 0. Once again, see the diagram. See, it is a pill box. Which field? Now field is coming like this, not coming like this. This is the field direction. So this direction is normal to the boundary, isn't it? Okay. Now see, it is this pill box is compressed. Then only this side area and this side area never 0, but curved area is 0. Okay, so both side area we take here. And now see here, this is a rho is taken, but pill box is a small substance, so that is why instead of taking rho, take its area, its charge density as sigma only, not rho. So sigma is what? Q by area. From this, Q is equals to sigma into area. Okay, so here only sigma term we have taken. Now see, what is this? D into, so this, see, this is K, we can write like this. Integral d dot ds is what? Simply Q. It is a Q. Okay, but this Q is, we have to take it as a sigma A only, this Q d, and take this d outside. Integral ds is equals to sigma A. So integral ds is small area, integral ds means total area is A. Okay, so left side we have to apply this formula, and right side also we have to apply. Alright, left side area is A, left side area of the pillbox is A, right side area of the pillbox is also A. Now see, left side is taken as negative, right side is taken as positive, and it is sigma A. Okay, now it can be written as like this: d2n minus d1n is equals to sigma y, because A cancel, A cancel, A cancel. So see, it is not equals to 0, it is equals to sigma, so that is why it is called discontinuous. If it is 0, then it is called continuous. If it is not 0, it is called discontinuous. Okay, that is the normal component of D is discontinuous at boundary. The change in the normal component of D at a boundary is equal to the surface charge density. So its change is equal to surface charge density. Okay, let me enter into the magnetic field. Yes, so for magnetic field also there are the two statements are there, boundary conditions are there. So already we have applied two equations, Maxwell's equations for the above two boundaries, and the remaining two Maxwell equations can be used here in magnetic field. Okay, let me start. In the presence of surface current at the boundary, the component of the magnetic induction parallel means tangential to the surface changes abruptly by an amount equal to the surface charge density. So when this word comes abruptly by an amount equal to current density, surface current density, means it is a discontinuous. You cannot get equal to 0, you get some value, that is J value get. Okay, so how? Consider a loop spanning, one loop have to consider, spanning the interface. Let H1t and H2t be the tangential components of magnetic field intensity. Why it is H is taken? You know the relation B and H. B is equals to mu naught into H. It is in free space, in medium, in dielectric medium, mu H, right? So in the place of B, it is H is taken. The component of magnetic field is right. Okay. The necessary boundary conditions can be obtained by applying the modified Ampere's law. By applying the Maxwell's modified Ampere's law. So it is Maxwell's modified Ampere law. Okay, friends. This we will take. And see, it is a boundary we have to take. See, boundary. This boundary is appearing clearly. Yes. So it is tangential. Here the magnetic field we have to apply like this. So through this also a certain field will pass on either side of the boundary. Then consider one loop. So that is why they have considered this loop. Okay, and loop this side as a delta x, and it is a width. This is the area is ds. Okay, now keep it like this. Now come to the formula. So actually formula of Ampere's law is what? Integral h dot dl is equals to what? Mu naught into I. It is actual formula. Okay, so it is also integral h dot dl. This in the place of this is mu naught into I. Sorry, when it is h, then you cannot get mu naught. It is not like this. When it is b only, then mu naught will come. So let me write both formula. Integral b dot dl is equals to mu naught into I. In terms of h, integral h dot dl is equals to I only. Why? If you bring mu naught this side, b by mu naught is h. So integral h dot dl is equals to I. It is I is called current, and current can be written as current density into area. Why? Current density is what? Current by area. Okay, but here we are not taking big much. Okay, then instead of taking area, simply take length only. So current J is equals to I by L we have take. Current density J is equals to current by length we have take here. Okay, so please keep in mind this formula. J is equals to I by L. Okay, from this I is equals to JL we can write. Yes, in the limit in which the width of the loop becomes 0, right? When the it is a boundary, just now we have taken like this loop. So if you decrease the loop when it is very near to the boundary, then its width becomes 0. The contribution to the integral around the loop h from the narrow ends becomes 0, right? So narrow becomes its total field also inside 0. Does the integral of d across the bounded area of loop is? So this side tangential field is h1t, this side tangential field is h2t, and this is we have take negative, and this is we have take positive. Okay friends, see, minus h1t. Why? How it is L come? Integral h dot dl is equals to, just now I wrote like this I, and I is also written as a current density into length. Just now I said you. So please keep in mind. So in the place of I, what we can write? In the place of I, okay, so what is the formula? Integral h dot dl is equals to I is equals to j into L dl. Okay, so take h outside, integral dl is equals to jl. So dl means small length. If we integrate, it gives total length, so that is why h into length we get. See, h into length. Here also h into length. In the place of current, JL is written. Okay, and this is the left side h, and is right side h. Left side h is always negative, right side h is always positive. So that is why here L and this L gets cancelled. So finally what we got? We got this is, see, is there this difference is not equals to 0. When the difference is not equals to 0, then it is called discontinuous. When the difference is 0, that is a continuous. Now, so that is the tangential component of h is discontinuous, but an amount equal to the surface density at the boundary. Okay, so discontinuous, and that is equal to current density only. Next, last boundary. The component of magnetic induction perpendicular means normal to the boundary is continuous across the boundary. Now it is continuous in magnetic field. Okay, in magnetic field normal component is continuous. In electric field tangential component is continuous. How? See here. Consider a pillbox across the interface. Let B1n and B2n be the normal components of magnetic induction in the two media at the interface. The necessary boundary conditions can be obtained by applying Maxwell's equation derived from Gauss law for magnetostatic. Integral B dot ds is equals to 0. So it is Gauss law in magnetostatic. Okay. So again pillbox we have to consider, right? And a B1n is the left side and B2n is the right side field. Which field? Normal field. And see the diagram. So this side B1n, this side B2n, normal component, and it is a pill box. Okay, and which formula you have to apply? Integral b dot as is equals to 0 formula we have to apply, isn't it? Okay, area is there. And when we compress this pill box, actually pill box at the beginning we have to take very much big in size, so this much of pill box we have to take, and this side area is A, this side area is A, and this curved surface area is also A. But when we compress two ends, then it becomes only this much small, then curved surface area is 0, but this side area and this side area is remains constant. Now come it here. So three areas we have to apply. One is left side, other one is right side. It is for curved surface, but curved surface term is always 0 when we compress it, when we take very near to the boundary. Okay. Now it is taken left side, so negative value, and right side is positive value is taken. So this minus this is equals to 0, right? It is a what? See, difference is 0 means this is a continuous. Okay, so that is the normal component of B is always continuous at the boundary between the dielectric media. So these are the 4 boundary conditions, and very important, and you never get this explanation in YouTube also. So that is why please watch this video again and again. Thank you very much.